All right, so old stuff, but with a new no calculator lens. All right, we are going to be looking at exponential functions. So on your notes, what I want you to do is, I know there's a lot of text and formulas sitting in front of you on the notes. You might want to highlight what an exponential function looks like. So it's buried kind of in your, we're on worksheet 1b right now. F of x equals a times b to the x power, this guy. This is an exponential function, so we're on side 1b. And then in Algebra 2, you probably saw it written more like this, where they put a multiplication dot between the a and the b. And we do that for Algebra 2 kids because they have a really hard time understanding that when I say who is the base, I'm referring to the variable b, the thing that's holding up your exponent. Okay. So a couple of rules about exponential functions to remind you of is if you have a base that is greater than 1, that means you have an exponential growth. And if you have a base between 0 and 1, you have an exponential decay. But then your Algebra 2 teacher, and I did this to my kids too, so I don't blame yours, it's all of us. They'd give you something like this. And they'd try to trick you. Is this exponential growth or decay? Why? So it means this, right? It means 3 to the negative first raised to the x power. And what does 3 raised to the negative first power really mean? Not negative 3, but 1/3, right? Negative first exponent means the reciprocal. All right, so 3 to the negative x power is really 1/3 to the x power. So that was a bit of a trick question. Can you guys look at this with some new pre-calc eyes for a moment? What transformation did you apply when you throw a negative inside with the x? It's a reflection over the y-axis, right? A horizontal reflection like this. So 3 to the x power is normally an exponential growth, but if you reflect it over the y-axis, don't you end up with this? So now with pre-calc eyes, you can realize, oh, that's another way of interpreting that. If I had 3 to the negative x power, that is a growth of base 3 who's been reflected over the y-axis. Okay. So keep that in mind. That we might try to trick you with that again in pre-calc. There's a lot of stars on this page, guys. That tells me that these are all things that, quote, you know already from Algebra 2. Okay. So an exponential growth, I think y'all know what it looks like in general. It grows as you go throughout the domain. Speaking of domain, domain is forever on exponential growth and decay. The range, however, is going to be stunted or stopped or possibly started by wherever the location of the horizontal asymptote is. Speaking of the asymptote, a normal growth and decay graph has a horizontal asymptote at y equals 0. Is it always going to be there, though? What kind of a transformation would move a horizontal asymptote? A vertical one. Very good. So if I moved it up or down, that would shift a horizontal asymptote. If I reflected it, that might change it a little bit because of the direction it's opening then. X-intercepts, there's going to be none unless there's some shifting happening. There's no extrema. It's very continuous. The end behavior is kind of crazy, though. One side of the end behavior approaches the asymptote while the other side goes to infinity. We're not going to use limit notation. We're going to use our regular notation today. It's always continuous. And everything is almost the same for exponential decay, except the nature of the shape changes a few things. So like, for instance, the end behavior is going to be opposite. So like on the left side, a decay is going to go off to infinity. On the right side, it's going to approach the asymptote. So are you able to graph these without a calculator? That would be my next question. And the answer is hopefully. So this one's already done for you. If this was my function and I was asked to graph this on my Friday's no calculator test, and guys, I mean like no calculator, like not even a scientific one, okay? You would have to come up with an XY chart on your own. So I know that strikes fear in some of your hearts, but I don't think it's really that bad. I know they already have the table over here, guys, but let's talk about how we could create an XY table for 1/3 to the x power. Well, with the domain going off to infinity and negative infinity, you don't have any restrictions on your x's, but that means that as a grapher, I would like some variety in which x's I'm providing. So I'm going to do the normal 0, 1, 2, but let's get some negative values as well. Let's get their negative twins, if you will. So you can plug these in whatever order you want, remember? And you're going to have to use the old noggin, not a calculator this time. So let's plug in a 0 into our function. Let's think about this, guys. If you take 1/3 and you raise it to the 0 power, raising anything to the 0 power gives you a 1. And if you take 1/3 and you raise it to the first power, you get 1/3, which I know is a decimal, but I'm just going to write down 1/3. And if you raise 1/3 to the second power, that's like you're squaring the fraction, so squaring a 1 and squaring a 3, you get a 1/9. Now, I can already tell you, I'm not going to be able to graph a 1/9. So it's going to pretty much look like 0, and that's okay. Now, the negative versions of all those x values, it's going to be the same fraction outputs, but because of the negative exponent, you're going to use that negative exponent rule that flips them around. So 1/3 to the negative first power is going to be 1/3 again, but flipped. So it's going to be a 3. And then to the negative 2 power will be the 1/9 again, but it'll flip it. It'll make it a 9. So you're going to have to come up with this table. I know y'all can plot points. I'm not ever questioning that skill of yours. But you have to come up with the table yourself. And then when you play Connect the Dots with me, you should see what you would have determined on your own without any assistance. You would have known that this was an exponential decay because of the base being smaller than 1. And when you connect the dots here and you graph it, you do get an exponential decay. Now, one thing to point out though, the intercept. This is the y-intercept. And I think some of you get really hung up on how do you find a y-intercept. You always find it the same way, no matter what your function is. For y-intercepts, you just plug in x equals 0. So if that's just a problem that you're doing in isolation, like if I threw a problem at you and I was like, quick, find the y-intercept, you just plug in x equals 0 and figure it out. But you already have the y-intercept right here. You already found it. So there's going to be some follow-up questions on your test on Friday, like it's going to say graph it, it's going to say give me all of this information. What's your domain? What's your range? What's your y-intercept? Is it continuous? By the way, is this a increasing or decreasing roller coaster? Decreasing roller coaster over its entire domain. So that's the good news about exponentials, is that they're either always increasing or they're always decreasing. There's no change of behavior. The asymptote, they call it the x-axis, but I'm going to ask you guys to go ahead and call it what it is, which is the line y equals 0. All right, let's see one that's not done. Oh boy. Now this is much harder than what I would give you on the test. Okay, on the test, I'm going to give you basically a parent function. There's going to be no transformations whatsoever to it. What would have been the parent function to this guy? Just the really boring one that doesn't have any transformations. Just 2 to the x power, right? So what we're going to do, if we were forced to graph this one without any graphing calculator help, I'm still going to want a t-table, but it's going to be off of the parent function. And then we're going to take all the points from the parent function and we're going to apply the 2 different transformations you see. All right, help me out here, guys. If you have x minus 1 in the exponent, what does that do for shifting? Is it right or left? It's right one. You all keep second guessing everything you know now. And then if I have a plus 1 outside of the body of a function, that's a vertical shift of up 1. All right, here's what we're going to do. We're going to come up with some ordered pairs for the parent, and then we're just going to move them. So, like for instance, I'm not going to get crazy with my points this time, guys. I'm just going to go -1, 0, 1, and 2. And if I plug that into the parent function, 2 to the negative first power is a 1/2. 2 to the 0 power is a 1. 2 to the first power is a 2. And 2 to the second power is a 4. I'm going to, if I was using pencil, I might just go ahead and plot these, but I'm going to very gently plot these because I'm about to move them. All right, so -1, 1/2 is like right there. 0, 1 right there. 1, 2, and 2, 4. All of those red points that I just plotted aren't actually my true function because y'all told me that I was supposed to take that parent function and transform it by moving right 1 and up 1. So everything I just graphed, I'm going to move right 1, up 1. Right 1, up 1. Right 1, up 1. And right 1, up 1. Now the other thing I have to watch out for, oh boy. The asymptote moved. Now the right one didn't shift the asymptote. It used to be located at y equals 0, but since everything was shifted up 1, that means you now have a horizontal asymptote at y equals 1. Very good. And if you were a careful grapher, which I clearly am not, you probably could have fudged that in pretty easily without doing a lot of work. So I just want to be clear, on your test on Friday, the ones that you're going to graph for me have no transformations on them whatsoever. It'll be like 2 to the x power or 3 to the x power. It'll be something horribly boring. Okay, the domain of every single exponential function. This is like my favorite question on the whole test. It goes forever, negative infinity to infinity. This particular one, however, has a range that's no longer at 0. Remember, everything got shifted up 1. So your range goes from 1 to infinity. Please notice that I used a parenthesis on the 1 because that's the location of the asymptote. So you're not actually getting there. Okay, intercepts. I don't know if I was paying close attention to where this y-intercept was, and if I wasn't, that's okay, because I think I could figure it out pretty quick. If you just plug in x equals 0 into your function, that's the y-intercept. So 2 to the 0 minus 1 power plus 1. So that's 2 to the negative first power, so it'd be like 1/2, plus 1. 1.5, yeah. So you have an intercept at 0, 1.5. Yeah, just write yourself a big note, right, guys? I feel like this might confuse someone who's just looking at my notes. This ordered pair is just the parent function. It wasn't the true function we were looking at. Okay, the asymptote, as you guys already pointed out to me, now is located at y equals 1. And then it's end behavior time. So we're going to go back to our normal left and right end behavior. And those of us who are still struggling, I want to see the word left and I want to see the word right. And maybe do a little color coding. So like for instance, as x goes to negative infinity, that is a fancy way of saying left side. So on the left side of your function, what height is it trying to approach? At 1. Very good. So it's approaching the asymptote at 1. Good. And then on the right side of the function, this means right. That's this guy over here. Where is it approaching? An infinity. Yep, it's going up, up, up. Okay. And then real quick, is this always an increasing or decreasing roller coaster? Increasing. So it's increasing from negative infinity to infinity. Cool. So much harder than what's on your test. If you can also graph a transformed one without a calculator, good on you. Oh, E. Do you guys know E is a number? So they use the symbol E to represent the number E, which is called Euler's number, and it's also known as the natural number. So you're like, what? Okay, so Euler gets credit for the number E, although I kind of have a feeling that Euler just gets a lot of credit for a lot of things because he was like a big dog back in the day, so I think his underlings actually discovered a lot of things, but that's okay, it's cool, Euler, you can get credit. Euler, they refer to this as the natural number because it's used a lot in a lot of natural applications. Like I think there's one coming up that's like a tide pool, like a whirlpool. The natural number E shows up a lot in nature, which is very interesting. It is an irrational number, and you probably don't remember it off the top of your head, but we usually say it's about 2.718. So if I ask you guys to graph the function y equals e to the x power, if you remember that e is roughly 2.718, this is roughly 2.718 to the x power. Would that be an exponential growth or an exponential decay? Growth, with a base being about 2.7 is greater than 1, okay? So if you have just the very boring e to the x power, that is technically an exponential growth. However, the one on your paper, and we're still on side, what are we on? 1B still? Why is this one decay? Got that negative exponent, so you can either think of this as an Algebra 2 student who tries not to be tricked or a PreCalc student who understands transformations. So if you think of it as a negative exponent, it really says this, which is going to be a decay graph. And if you want to think of it as a PreCalc student, It's a growth who was reflected across the y-axis. And that's why it's showing up as a decay. All right? So either way, the parent function is e to the x power. At no point would I be like, hey, y'all, here's a no calculator test. Please work with the number e. No, that is not something that we would ask of you. If you want to identify a transformation for me, though, now with PreCalc brain, I think we could. We're going to say it's a reflection over the y-axis. I almost did it. That was bad. You could also call it a horizontal reflection. I'll accept that. I do not expect you guys to do any of this without a calculator, because 2.718 blah, 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 blah raised to various powers is nothing pretty. The only two that I can come up with without a calculator are if you plug in a 0, you get 1. And if you plug in a -1, you'll get back the number e, which is approximately 2.7. So -1, 2.7-ish, and everything after this point, like I have no clue what the numbers are, because I can't do that in my head. But I can totally fudge in a graph. I already was told this was going to be a decay, and there's no vertical shift, which means the horizontal asymptote is going to scoot down here. Whoops. You get the idea. So the domain, that's an easy peasy question on every part of today, because domain is always negative infinity to infinity. The range was not affected by that transformation, so the range still starts at the asymptote at 0 and goes to infinity. Just make sure you guys are using a parenthesis on 0, not a bracket. The intercept, I think we kind of stumbled upon. There was no transformations that affected that original intercept, so when you plugged in x equals 0, you got a 1. The asymptote wasn't moved off of y equals 0. All right, let's talk about end behavior. I want your left and your right behavior. Whoops. So I tend to go left first. Just good for me, because I'm dyslexic. All right, so left is going up, 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 up. We call that infinity. And then on the right, which is this, it's trying to approach a height of 0, yes. So you might recognize something from Algebra 2. Your teacher hopefully pointed out to you guys that the vertical shift, k, was very important to these questions. So that vertical shift obviously is a vertical shift if you have one, but it moves the range, it moves the asymptote, it moves the end behavior on one side. So we did a lot of highlighting in Algebra 2 where, like, if it had a +4 off the back end of the graph, you would see that 4 show up like a whole bunch of places in this next part of the problem. Okay? And is this an always increasing or decreasing roller coaster? Decreasing from negative infinity to infinity. Very good. All right, let's flip over to 2a. Now we get to the good stuff. It's not a nap. We're going to talk about bacteria and money. Two things that really kids are passionate about. So you will have a formula card. I forgot to copy it, so my bad. So you'll get that tomorrow. You'll also get a fresh one to take the test with, a formula card if we need to use formulas. And these formulas, these three at least, should all be familiar to you, although they are using like a more advanced notation from PreCalc rather than Algebra 2. So like for instance, the exponential growth and decay formula right here, when you guys were in Algebra 2, you saw this, a and then 1 plus or minus r to the t power. Does that sound familiar? Yeah. Okay, so a was the original amount. They're using n sub naught in PreCalc because n meaning initial value. When they put a sub naught, it means initial. So that's just like more like college level notation. They like to mess with you when you get to college, okay? So notice the other thing they don't do is they don't say plus or minus, because they know that you guys are smart enough to recognize that sometimes a rate is positive and sometimes a rate is negative. And it has to do with the nature of the question. So like if you're growing or adding money to an account or population is reproducing, that's a positive rate. And if you're depreciating, decaying, spending money, something's happening where it's dying off, they're going to have a negative rate. So they don't make a convoluted looking formula because they know you guys are smart enough to figure it out. Now this guy, everybody's favorite, this is the PreCalc version of it. This is the Algebra 2 version of it. It's your friend PERT. And you know to use PERT when it says something is growing continuously or decaying continuously. Continuous exponential growth and decay. We're going to see something new today that I think might be new for everybody. I don't think honors did it either. You can continually decrease at a certain rate too. I don't know if you guys ever had to do that in honors. So we'll talk about that later. Notice P is what you used in Algebra 2. They use n sub naught again. But who's the base here, y'all? E. It's your friend E, that 2.718 blah, 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 blah number. Okay, so continual growth or continual decay is going to have a base of E. And then this formula should look super familiar. Used it a lot in Algebra 2. This is when you're compounding over a certain number of times every year. So they might say things like compounding monthly, daily, weekly, semi-annually, bi-weekly. Yeah, that's a hard one because kids are never really sure what that means. What does monthly mean? So the n is the number that keeps changing depending on how often you collect interest. So what does monthly mean for n? 12, good. What about quarterly? 4. What about weekly? 52. Semi-annually? Twice, good. That means twice. Daily. We'll go with 365. 365 and a quarter is the technical answer.
Yeah,
Leap year,
how long
man.
is 1 day, actually?
I know, it's all these things. Yes, Miss Pipe. Yes. So if it ever says daily, just go with 365. Don't get crazy, okay? Let's take a look at some examples. This is where you're going to be like, I loved these in Algebra 2. Okay, so you might be wondering, I very much remember using my calculator quite a bit for these in Algebra 2. Yeah, and you're going to use that quite a bit in PreCalc as well. So the difference is on our test on Friday, I'm going to ask you to create the formula, and then that's it. Walk away from the question. I'm not going to ask you to evaluate the formula. I don't expect you to take like 6,700 times 1 plus 0.05 over 12 to the 12t power. Like, no, that's not something you should be doing in your head, okay? So let's take a look at this example. It's a good old colony of cells, and the original amount in your colony is 100. So you're going to be placing that right here in for the original amount. So in the parentheses, you start off with 1. That would be like 100%, no change. But this colony is reproducing at a rate of 25% per week. So reproducing, meaning it's going to be increasing. So plus, and then you have to write this as 0.25. You got to make sure it's written as a decimal version. And it's measuring, keep note of what the time values are. Sometimes they get sneaky in PreCalc. This is per week. And they do keep the same label on my time later on in the question. So 6 weeks later means you're going to be plugging in a 6 for the variable t. So on your calculator, please, this is just in your home screen. I need y'all to type 100 times the quantity, 1 plus 0.25. Of course, you can change that to 1.25 to the 6th power. We are only raising that base of 1.25 to the 6th power, though, guys. So don't do it in stages. You got to type it all in at once. And I know there's cells, and you don't really care if you round off a cell or not. Just round to the nearest whole number in this case. You should get about 381 cells. Yep, we're just in the home screen. Alright, so money. Let's talk about money. Lance has a bank account. Now, I want to know where this bank is. He has 5% interest rate. Okay, that is not a thing. And it's compounding continuously. Now, in algebra, 5% is kind of crazy high. Yeah, maybe they take 5% of your money, but they're not going to pay you 5%. Okay, so he's going to invest $1,000. That's the original amount. That's the P in this formula. And then continual interest means your base is E. But up in the exponent for E, you're supposed to write 5%, which is written as 0.05. But you got to multiply it by how long you're letting the money sit. So I think it says 10 years somewhere in the problem. So times 10. If you're on a newer calculator, all of this is up in the exponent and you just stay there. If you're on an older calculator, please use parentheses around the 0.05 times 10 part. And this is money. So an appropriate place around your money would be the hundredths place. So I think you get $1,648.72. Can we get a confirmation on that? He's just rolling in the interest. My goodness. That's crazy. Now notice it did say there's no deposits or withdrawals, so like he didn't touch the money at all. Because I don't know if you recognize this from Algebra 2, but if you do add money every month, or if you take any money out of it, you've completely changed the balance of the account, and it's a big difference. We're going to be using a really cool app on your calculator next week that helps you find that question, because that's real true life, right? Like very few people say, here's $1,000, don't touch it. Like that's not what happens. But like for me, like my kids have their 529 account, and we might put a lump payment in to start off, but like every month we add so many dollars, you know. So that changes things quite a bit. Continual growth of the account is going to make a big difference. All right. So let's do a couple more practice problems. These should feel very Algebra 2-y. You should be like, yes, I totally remember doing this. I mean, I don't know if you liked doing these, but... Okay, so this one they actually want you to compare. All right, so we are going to compare two bank accounts. We have continual interest versus quarterly. All right, so $5,000 we're investing in both accounts. For the continual interest formula, you're multiplying it by a base of E, and then you're raising it to the, watch your decimal point, this is 0.085. And then we're leaving it for 10 years, so times 10. However, for the quarterly account, you start off the same way with $5,000, but your base is not E, it's a quarter installment. So the way the formula works is you take 1, and then you add your interest rate, which is 0.085, but you don't get all 8.5% of it 4 times, you get a fraction of it, right? So they divide it by 4. And why did I come up with 4, by the way? Quarterly, good. And then up in the exponent, that quarterly number shows up again, and you multiply it by 10, because you're going to collect quarterly 10 times. Okay? So again, if you're on an older calculator, make sure you put parentheses around this 4 times 10 part. Everybody needs parentheses around the entire base itself. Let's compare these two accounts, and let's talk about that. I'm going to write down what I got, and you tell me if it's wrong. All right. They're pretty close to each other. I mean, the continual interest one has more money in it, which should not surprise you. If everything else is the same, and you collect interest more frequently, you're going to have more money at the end of the problem, if nothing else changes. What might surprise you, and what really boggles the mind of the Algebra 2ers, is they're like, what do you mean I only have like $100 extra? Like, this doesn't make sense. If you collected interest all the time for 10 years, you should have way more money. But that's not really how the math works, right? You don't get a full interest payment like every second of the day. They take your interest and they subdivide it into little teeny tiny chunks. So you do end up getting more money because you're building money on your interest at a higher rate. Or more frequently, I should say. But it's not as substantial as people want to think. I mean, it's more. And if you let the money sit for 20 years, or if you invested more money, you would see a much more substantial difference. But not much. All right. Oh, this one. Okay, so we have an estimation from the year, it doesn't say, in 2007, an estimation of 101,000 quadrillion thermal units were used. Okay, so we're not going to use quadrillion into our numbers. That's a lot of zeros that I don't want to work with. So just as we get answers, I'm just going to smack the label of quadrillion to it. So we're going to start with 101,000. That's the initial value. And it's increasing at a rate of 0.5% annually. So I'm going to use the more boring looking function, the increase one. Because it's annually, you would just be dividing by 1. And this is, I think, something, now that you're pre-calc, you can understand a little better. If I go back to these formulas, I would argue that these formulas are actually the same formula. The only difference is compound interest. If you have an n other than 1, like quarterly, daily, weekly, you have to divide the rate by that and multiply the exponent by it as well, because you're collecting the interest more frequently than just once. This is like a very simplified version of that formula where you just collect it once. So dividing by 1 doesn't do anything and multiplying by 1 doesn't do anything. Okay. So I'm going to use the simpler looking formula because it's simpler. And then we're increasing. Now careful here, guys. 0.5%. You'd move the decimal over 2 times and you get 0.005. And what am I supposed to put in for time? Because it increases annually and I go from 2007 to 2020. 13 years. Very good. All right. So on your calculator, I think this come out to 107765. What label am I putting on this? Quadrillion thermal units. Quadrillion. Sounds like, yeah. It's a lot. I don't really know what a thermal unit is, though, I'm going to be honest. It's just what they're measuring their energy in, I suppose. Okay. And then everyone's favorite question, rabbits. What happens when you leave rabbits unattended? Also, same thing that happens with hamsters, gerbils, and other rodent-type things. They get busy. Well, then you know. Now, we'll find out next week that this problem doesn't really make sense, because if you think about it, if you left like a colony of rabbits on a deserted island, they're not going to breed indefinitely. Like at some point, nature's going to kind of take over, and there's only so many resources. So like, there's going to be a point where they'll kill each other, or there'll be no food. Either way, that's a next week problem. That's called a logistic growth problem. Today, let's just pretend that rabbits are doing what rabbits do. Okay, so these rabbits that increase at a rate of 10% each month. Now watch your labels. This is each month it's growing. And we start off with 10 rabbits. And we're increasing 10% each month. So 0.10. And then this was last year. So how much time am I plugging in here for T? But it grows every month. There we go. So the time we're going to plug in is a 12. Now some people are like, oh, I could do the compounded formula and use like 12 for monthly. It's going to work out the same way, so I'm just going to do it this way. All right, anyways, how many rabbits we got? And these are rabbits. Let's round in here. It's whole rabbit. 31 rabbits-ish. And then you blink and all of a sudden it's 34 rabbits. Oh, rabbits. There's actually a really cool Fibonacci problem associated with rabbit breeding. All right, move on. Worksheet 2. B. Okay, these are humans. So the population of a town is declining at a rate of 6%. If the current population is 12,426, predict the population after 5 years and 10 years using 2 different models. So we actually have 4 problems hiding in here, guys. If we're we're not collecting people. So if our population is declining annually, we're just going to use that really boring formula. So it starts off with 12,426. And then because it has the word declining, also known as depreciating, that means you need to subtract 6%, right? So you are welcome to set it up as 1 minus 0.06. And then some people will say, can I just call that 0.94? And yeah, of course you can. Now, I want you to do this problem 2 times. The first time with t equals 5. And then do it again with t equals 10. And I need the population of the town. Now, this is where I wish more kids would just use their brains. If you wrote your formula wrong, most common mistake is kids put 1 plus 0.06. Your population is going to grow and grow and grow. When if you go back and reread the question, you're going to be like, well, that can't happen because it's supposed to be declining. All right, so plugging in a 5. These are people, so let's round to the nearest person. I got 9,119 people. Cool. And what about 10 years? Is it about 6,000 something? 6,693? Okay, and since we're only answering the 2 questions, it wasn't worth our time to like program our table because you're just answering 2 questions. All right, same idea, but this time we're collecting, we're not collecting anybody, okay? Our population is declining continuously. So this is the one where I think this might be new for everybody. So you start off with the original amount, continual means our base is e, but up in the exponent, because it's declining, you need to call your rate what it is, which is negative 0.06. So negative 0.06 times, and then again you're going to change the t each time. So the t, the first time when you plug in a 5 to this, make sure you have a negative in the exponent there. That will create the decay factor. I think you get about 9,205 people. And then 10 years, you get 6,820. Make sure everybody knows how to type these in, because that's kind of half the battle on this test, right? When you come up to the typing test is, I can't help you with the calculator. Like, I'm asking you how to use the calculator, not the other way around. All right. So let's take a look at the final question. This is probably the most challenging question for kids because it's atypical. We have some data from a census. Do we need to go back? Okay. Data from a census where they only collect data every 10 years, and that leaves a lot of like gaps data there. So they want to know about all the in-between years, and if we can create a model that represents like the annual rate of growth for this population, for this county within those years. So I have to identify the rate of growth. The problem is I don't have a year-to-year piece of data. So it's not as simple as, oh, just take the original and divide by the new one, and boom, there you go, rate of growth. Not quite. Here's what's happening. We're going to pretend like time starts in 1990. Which means if I use this formula, my initial amount, if you want to call it that, is 1.94 million. Now, I already know R is going to be a variable because that's the question. It says, what is your rate of growth? So I don't know, leave it as R. But there's another piece of information here on the table. How many years later are we measuring data now? 10 years later. So I'm going to plug a 10 in for T. And then when I look ahead in 10 years, what's my final amount? What would my, quote, answer be? The 2.25. So guys, this is the equation we have to solve. 2.25 equals 1.94 times 1 plus R is a quantity to the 10th power. So in order to solve this, it's going to be gross. I'm going to divide by 1.94. It's already gross. And you don't want to round this off too much, guys, because you really change your answer. So 1.1598. And then it's times the quantity 1 plus R to the 10th power. And this is where kids freak out because they're like, how do I get rid of a 10th power? Well, two ways. You can either 10th root it using your x root on your calculator. Can't you multiply it by the reciprocal, though? Can't you raise it to the reciprocal power? Can I just raise it to a 1/10th power? As long as I do it to both sides, right? That's the rule of math. So over here, they just cancel each other out. But the 1/10th power is the same thing mathematically as taking the 10th root. Okay, obviously you need a calculator for that, guys. This comes out to 1.01494 roughly. But it equals 1 plus R. So your final step would be to subtract 1 from both sides. So at this point, now would be an appropriate time to round. Your annual rate of growth is about 0.015 or 1.5%. So with that in mind, I can actually write a model. I'm going to decide to start the model in the year 1990. So it's going to start with 1.94. And then we just said it was growing at 1.5%. So inside of the model, it's going to be like 1.015. Where did I get that from? 1 plus 0.015. There we go. And then to the x power or to the t power. This, children, this is your model. So then there's a follow-up question, which next week we'll talk about how I want you to solve it like the most accurate way possible. For today, we're just going to be using our calculator, not your table though. Okay, here's what I want you to do. Please type in Y1, please type this function. And then in Y2, please type your target value of 2.7, which represents 2.7 million. And then when you adjust your window a little bit, guys, you're going to see an exponential growth, and then you're going to see, a constant function at 2.7. And your job is to figure out where they intersect. Because at that point, the population will be surpassing that value. And the answer is right there, which is at approximately 22.2 for x. But only a psycho would run around going, x equals 22.2, see ya! Did I just offend you? So, 22.2 is years. But when did time start in my problem? 1990. So if I'm 22.2 years later, I'm sitting at about 2012. So in the year 2012, 7 years ago. So this is a really stupid problem. Because we have data where we could just go look. That's called interpolating, where you look within your data. Maybe you have incomplete data. Extrapolating would be looking out into the future, which is usually what they use this for. Alright, so the most challenging part of that question is finding the annual growth rate. That's on your homework. And it's also going to be not on this Friday's test, but an upcoming test where you have to find the interest rate using that. Alright, this is your homework. Do them. I know you're looking at that homework going, oh my goodness, this looks very long. It does look very long. This assignment is pretty much what you saw in the notes. The next few assignments, I know they look very lengthy. They're very quick because it's a lot of no calculator inference questions, okay? All right, stay up on your homework. I want to see way more homework checks than I just got on this last one, please.